Okay, it's time for the chain rule. So we will be able to integrate composite functions. So something like the square root of x squared plus 1. So remember, a composite function is where you take a function of another function. We think of inside functions and outside functions when we're talking about composite functions. So we take the derivative with respect to the outside function first, and then we differentiate the inside function. So it can be written in prime notation. So the derivative of f composed with g is equal to f primed of g of x times g primed of x. Or you can write it in Leibniz notation, so that dy dx is equal to the derivative of y with respect to u times the derivative of u with respect to x, where y is equal to f and u is equal to g. I usually just talk about inside functions and outside functions. So let's jump right into example 1. Capital F of x is equal to the square root of x squared plus 1. And of course, I like to write my square roots as rational exponents. So x squared plus 1 to the 1/2. So I have an inside function here that's living inside that set of parentheses. And then my outside function is the square root. It's the 1/2 power. So my derivative, first thing I do is I think about my outside function, which is taking the 1/2 power. So 1/2 falls down. Inside function stays exactly the same. Subtract 1 from the exponent. Now we've dealt with the outside function, we look at the inside function. The derivative of the inside function is just 2x. I'm happy with you leaving your answer just like that. You don't have to simplify it at all. If you're offended by negative rational exponents, or you just really want to cancel that 2 with that 1/2, you could write this as x sits on top of the square root of x squared plus 1. But it's not necessary. I'm happy with the first way. And there's the pretty answer. Chain rule is really important with the trig functions because we're often taking a sine or cosine of something that's not just plain old x or plain old theta. So if we have the derivative of the cosine of a function, cosine would be the outside function, and then we would multiply by the derivative of that inside function. Similarly, we often have a power rule like we just did here. Anytime you have a power rule, you're just going to have that power fall down, subtract 1 from the exponent, and multiply by the derivative of the inside function. Let's look at another example. Y is equal to x cubed minus 1 to the 100 power. Now, if it were squared, you could just FOIL it out and then differentiate it piece by piece. But there's no way I'm going to multiply x cubed minus 1 by itself 100 times and get a 300-degree polynomial. I just don't have time for that. So chain rule says that Inside function lives inside the parentheses. Outside function is raising stuff to the 100th power. 100 falls down. Subtract 1 from the exponent. Multiply by the derivative of the inside function. You are done. You don't have to simplify it any more than that. Of course, the book does. Okay, here's some more examples. I'll leave 8, 9, and 10 for you to do since we didn't do any trig ones. I'm going to do 11 and 12 for you because they look a lot alike, but they're really very different. I'll leave this side of the page for 8, 9, and 10. So f of theta is cosine of theta squared. So this time, cosine is the outside function. Squaring stuff is the inside function. So first we think about the derivative of cosine. That would be negative sine. Inside function stays the same. So negative sine of theta squared times the derivative of this inside function. 2 falls down. Subtract 1 from the exponent. So cosine was outside, squaring stuff was inside. Number 12, we have g of theta is equal to cosine squared of theta. So we have to think about that notation. Cosine squared of theta means putting parentheses around cosine of theta and squaring the whole darn thing. So that makes it more obvious that cosine is your inside function and squaring stuff is your outside function. So g primed of theta, modeling good behavior, labeling my answer. 2 falls down. Subtract 1 from the exponent. Then multiply by the derivative of the inside function. Derivative of cosine is negative sine of theta. Easy enough. Let's go ahead and do number 13 because we haven't done with it one with an exponential or with a product rule yet. This is going to require both. So y is equal to x squared e to the negative 3x. Going to go ahead and label them first and second. First is x squared times the derivative of e to the negative 3x. So, doesn't look like inside and outside functions. But if you have e raised to a function, then e is your outside function and the exponent is the inside function. If you've ever worked with Excel, in Excel, e to the x is written exp, open a set of parentheses. So exponent, exp, is your outside function, and then what you are raising to the x power is your inside function. So I'm going to put parentheses around this. Derivative of second. The derivative of e to anything is e to anything times the derivative of the exponent is negative 3. Now I'm going to mark that off so it doesn't confuse me. I've done first times the derivative of second. plus second times the derivative of first. You may leave it exactly like that as far as I'm concerned. If you were needing to set it equal to 0 and solve, then you would not want to leave it like that. But for now you can. So I'm going to pause and I'm going to catch up and do those examples. All right, we can compare answers on 8, 9, and 10 now. 8 and 9 were pretty easy. Number 10, the trickiest part was remembering that cube root means 1/3 power. Being on the bottom of the fraction bar means negative exponent, and then you had to subtract 1 from negative 1/3, so you had to do some fraction arithmetic. Now we've learned our favorite derivative rule. The derivative of e to the x is e to the x. Now we'll be able to find the derivative of any number raised to the x power. First, we acknowledge the fact that if we have b to the x power, it could be written as e to the natural log of b in parentheses raised to the x power, because e and natural log undo one another. So e raised to the natural log of b power is just b. They are inverse functions. So this is equal to e to the natural log of b times x. So if I want the derivative with respect to x of e to the natural log of b times x, first thing I do is just rewrite it exactly the way it is. Then I multiply times the derivative of the inside function, in this case the exponent, and the derivative of natural log of b times x is just natural log of b. Because remember, natural log of b is just a number. We treat it the same as any other number. But this is b to the x. So the derivative with respect to x of b to the x is equal to b to the x, so just copy it down, times the natural log of the base. Notice that that rule works for e to the x because the natural log of e is equal to 1. So, quickie example, 2 to the x, the derivative of 2 to the x is 2 to the x times the natural log of 2. We'll take a break here. I'm going to come back and do these examples. So practice these, and then we'll go through a couple of them together in the next video.